So this has been developed in the context of the project NEXTGEN. It's a European project, Horizon 2020, collaboration with the University of Exeter. KWR is never too far, so it's actually also in that project too. The game, you can play it online if you've got a laptop or a desktop. Use a web browser, a recent one, preferably. You go to the Aquatech Innovation Forum. I'm going to click the link here. If you go to the Aquatech Innovation, there is something called Safe Aquatech Town, and we've made a little version of the game for them available. So if you click on that link, it will redirect you to some sort of introduction. You got different types of way to play the game, scenario with problems, and then you'll be redirected to a link that looks like this. And this is our game, working in the web browser. So there is a lot to describe, and for those of you which do not have eagle eyes like me, we need glasses or anything, you might need, we have a dark, extremely dark screen happening.
Let's leave it in.
That's, I was going to say that would be a short demonstration. It seems that your system likes and dislikes my game from time to time. So, all right. Let me get into it. We've got very little amount of time. So, yes, no, yes. Basically, the goal of the game in here is to increase your circular economy score, the stuff at the very top. What happens is circular economy is made of a lot of different things. And when we click on it, you can see a lot of little indicators, things like the water demand you meet, the reservoir stress, the level of stress in your reservoir, the level of water reuse, things about energy, your energy footprint, how much energy reuse you can do through biogas generation and other different things. Also, material reuse is part of circular economy. A little bit about the environment. We got another aspect about the amount of pollution you got downstream in the river, and also your environmental flow, how much water is left for your river ecosystem. And finally, we got a financial aspect to the game. So how much does it cost, all that? And also, do you have a return on investment for the next 20 years or not, depending on the type of technology you implement? So we got Toy Town. Very quickly, all the components in here are linked to each other. So at the top right, you got the reservoir. It's alimented by rainwater and the river flow. It brings water to the drinking water treatment plant, which in turn brings water to these 3 different neighborhoods. And we can change, using sliders, the size of the neighborhood and try different types of technology. Let's say in 1/3 of the town, implement one type of technology, another third implement something else, and see what the effects are overall. Once the water is used in the household, it becomes wastewater, and it's then treated in the big, well, I was going to say, in the big brown box that you can now see at the very bottom, which is our primary wastewater treatment plant. Now, there's a lot going on. We have a simulation engine in the background that simulates on a daily basis for the next 20 years, gives you a result in under a second. So as a user, if you change something in the system, you immediately see the consequences. For example, our population is 300,000 inhabitants. I'm going to be, let's go crazy, I'm going to double our population. So click on 600,000, and now we're going to see, oh, there are things that start lighting in red. The water demand met. For example, we measure that, it's a little indicator in percentage, but it tells us that the percentage of years during which there is more than 10 days in a particular year in which the reservoir is nearly empty. So you cannot meet water demand in your town. And the reservoir stress tells us things like the percentage of year during which there's at least 10 days during which the reservoir is less than half empty. So we got lots of little indicators. For example, we came up with little homemade things like the pollution index. It's basically derived from the number of uncontrolled discharge that result from what's happening in our system. And we measure roughly speaking, the cumulative depth of oxygen with COD that we develop in the river by discharging nutrients. So everything, it's a system which is on edge. And it's not, water is not infinite. Everything is impacted, energy footprint, everything. So you can change technologies. For example, at the household level, what could you do? You could change the type of toilet. You could change the type of, let's say, a shower head, something as unassuming, technology-wise, as a shower head. We can put a fog shower and see what's the impact on the whole town. Let's imagine we put our fog shower, and let's see what happens to our water demand. Instead of only meeting 35% of our water demand, we meet 65% just by changing a shower head. We also notice that it has an impact on the environmental flow. Before, because we had doubled our population, we only had 50% left in our river environmental flow. Now it's 57%. And we just changed this ridiculous shower fog head thing. Well, there are lots of other components we can change in there. We can try combinations of things and see what works, what doesn't work. We can also experiment on water reuse technology. Now, what would happen if we use rainwater reuse in every house in our town? So if I click on rainwater reuse, wow, we meet 80% of our water demand. Reservoir stress, well, it's a bit less stressed anyway, and our pollution went down. And I can compare what happened instead of using rainwater reuse, I use greywater reuse. Well, it's even better for water stress, but on the other side, our pollution didn't go down as much. Then we can start observing the behavior. We can ask why. Why didn't it go down? Well, it's because when we use rainwater harvesting, we introduce more water in the system, and therefore we dilute a little bit the wastewater when it comes to the river. Well, in the case of greywater reuse, we don't necessarily do that. It's a little bit more concentrated. So downstream, we get a higher pollution. Now, we can start analyzing the behavior of the system. We can also discover things about what's the most economic way to counter pollution. So perhaps we should connect house to sustainable drainage system, basin that can absorb some of the rainfall. So you can see your pollution, instead of being 40-something% when I activate connection to a basin that can absorb rainfall, the sustainable drainage system, it becomes 11%. If I click on the detail, you can see the number of uncontrolled discharge, the CSO event. Without connection to a sustainable drainage system, 195 a year. With a connection, in our toy town, 53 CSO events. So we can analyze, we can put things together, and we can even sometimes have a little bit of a surprise. We got a surprise by connecting bits and pieces together in our model. We found out the following, that the biggest, one of the biggest thing you can do against carbon emission is to look at metals in wastewater. So what we looked at is, I look at the material reuse at the level of the wastewater treatment plant, and you see in blue, the text is a little bit small, so some of you might have to get a little bit closer to see what's going on. But if you look at the metals that you find in wastewater, if you manage to retrieve 85% of the traces of metal from domestic wastewater, if you convert all that to carbon sink in the energy you save, because you don't go mine this metal and refine them somewhere else and transport them, then this is the equivalent per year for a town of 300,000 inhabitants of planting 5% of the surface area of the Netherlands every year in forest. But even better, if you take into account industrial wastewater, you mix it with your domestic because the concentration of metals are 10 times higher, you actually come to the startling conclusion that for a town of 300,000 inhabitants, recover 85% of metals, industrial plus domestic wastewater, it's like planting 50% of the surface area of the Netherlands every year in forest, carbon capture-wise. You change your circular economy score masterfully when you take that dimension of the problem into the equation. So it's good for policymakers because they get introduced to the idea of what a sustainable drainage is and what is useful for. And if it's more or if it's less expensive than building more pipes under your town, for example. And it's also good for, well, my son is 7 years old. He came to the conclusion faster than some of the people that play the game. So that's kind of good too. And, well, surprisingly, it's good for engineers. We noticed that not everybody has an overview of all the connective bits put together. Energy, wastewater, metals. I mean, metals is a bit that people don't necessarily always touch in the domain of wastewater, and similarly, energy is something different. So we have somehow reached our goal on creating a platform available to you all online for engaging policymakers, citizens, and possibly businesses, because there is a business case about, for example, one aspect of the problem, which is metals.
Thank you very much. Very exciting. I'm going to talk to you whether we can use it for our students at the TU Delft as well. I think it's a nice introduction in the whole urban water cycle, let's say. And so let's discuss that later. But I think with my first question would be, that's always the best thing of games, is talking about the rules. And the best is changing the rules during the game. Is there possibility to, because you said something like rainwater and grey water, etc., but it is all about the algorithm what's behind, and that you can discuss. Is there a possibility, an open platform also, to discuss about these rules and whether they are valid in different countries in the same way as it is in the algorithm? Or is it fixed and, yeah, should it be seen as a black box for us?
Actually, we implemented it in a way that we have a simple, not so simple, but a script that runs everything from a text file, which is a list of parameters. And some of these parameters can be modified directly in-game with the sliders, but others are fixed inside the text file because they are too obscure for users to actually be worried about. But yes, we can change the price of the water, and that will have an influence on your return on investment for your water bills, for example. We can change all these aspects of the system. We can add additional parameters too, but as you probably are aware of, that means extra work. But the way we've built the model behind it, it's modular. So we have one case study, which is our toy town. So it's very generic on purpose, but we also have two other case studies coming. One is about Greece, another one about Costa Brava. In the case of Costa Brava, we add a module about desalination plants, about salt intrusion to the model on top of the town.
Okay. So we can work with students on an improvement of or an extension of the system as well. Okay, very nice. Other questions? Yeah, Gertjan?
Thank you for your interesting presentation and the interesting game as well. I was wondering about removal of trace metals from the effluent that you made a plea of. Is it technologically possible to separate all those trace metals from each other? Because you can only value them if you have them in a pure form.
Well, that's a good question. So the technology doesn't seem to exist. I actually went yesterday to all the booths in Aquatech. I took my time, one after each other. Do you guys do metal mining from wastewater? There was no answer for all the metal that we're looking for. But what happened, what we found in the results was, you don't need to recycle all the metals. If you want to save most of the energy and carbon emission, you can target around 6 or 7 metals. Even so, it's a challenge. Apparently, from my poor understanding of the field, there is 2 branches, one being some sort of ionic resin way of doing things, but that doesn't handle very well high volume, like a town wastewater in flow. And others which are like activated carbon, but don't seem to be there yet. So there is a case to do something about it, but the technology remains to be developed. This being said, when you talk to a mining engineer, he will tell you, well, you don't have to go excavate the material somewhere in the Earth core, so it's certainly less energy intensive, but it remains to be seen how energy intensive it still is.
Okay. Okay, thank you. Last question? No question? We all need coffee. Thank you very much once again for your interesting presentation, and give him a hand. And then